Hi everyone, I'm Sandy Lucas, the Program Manager for the Climate Variability and Predictability Program at NOAA. Thank you for joining us for this webinar series called The Years of Maritime Continent and Piston Field Campaign. This is a continuation of a series of webinars for the CVP program that started several years ago. Today's webinars are being recorded and will be available from the CPO website under the Climate Variability and Predictability section. If you've missed any of the prior talks in past CVP webinars, I encourage you to view them from the website. All sessions from this series are now posted. The Years of Maritime Continent is an ongoing set of international field campaigns and modeling efforts focused on the Maritime Continent region. YMC is led by the countries of Japan, Indonesia, and the US in partnership with several others. Of particular interest to NOAA and the Climate Variability and Predictability Program is to improve understanding of processes that affect the propagation of interseasonal oscillations, such as MJO, in the Maritime Continent region and its broader regions. MJO is important to local weather and climate, as well as having global teleconnections. However, the Maritime Continent region can sometimes act as a barrier to those propagation, and weather and climate models have a hard time reproducing the effects. In response to that need, the CVP program solicited for observation and modeling projects that investigate different processes that affect MJO. Additionally, in collaboration with the Office of Naval Research, CVP supported several activities of the Piston Field Campaign. This year's webinar series covers the 16 projects funded by CVP. With only 2 sessions left, we are coming towards the end of this webinar series. I would like to ask you to save the date of April 8th at 4 p.m. in Eastern, which is our regular meeting time. On that day, I'd like to have an open roundtable discussion about the current state of this research and what gaps still remain. This meeting will be led by Chidong Zhang, and I welcome input from all of you, including those not directly funded by the CVP program. So just to repeat that, please save the date on your calendar for April 8th, 4 p.m. at our regular webinar time. More information will follow later in this month. Additionally, if there's interest in continuing this webinar series as a community-led effort beyond March, please contact me and Victoria Breeze. Our email addresses are on this slide. We're looking for volunteers to organize future speakers and dates. I may have some speakers lined up already for April 22nd, which interestingly enough is Earth Day. So your duties should you volunteer, if you're a postdoc or a graduate student or someone looking to meet and network more with the YMC community, please email us, contact us, and we will get you set up to lead and organize these webinar series. Sorry. I'd like to thank Dr. Victoria Breeze, our communications specialist, for her continued support during this series. Victoria will be describing the series and introducing our speakers today. Victoria, whenever you're ready.
Thank you, Sandy. Hello, everybody, and welcome to the 9th of 10 webinar sessions on the topic of Years of Maritime Continent, which will feature 2 presentations per session and runs from September 10, 2020 to March 25th, 2021. As Sandy said, an open discussion forum will follow on April 8th. This series of presentations will share the latest results from these projects and will allow the PIs to discuss the importance of their work, outcomes, and lessons learned with the broader scientific community. We hope you will enjoy today's talks and ask plenty of questions. As you listen to the presentations, if you have a question you would like to ask the presenter, please raise your hand. Raise your hand is a feature which you can find on the control panel for GoToWebinar. At the end of the presentation, I will unmute those who have raised their hands so that they can ask their questions using audio. If you have audio problems, I will ask you to please type your question into the questions box, which can also be found on your control panel. Our first speaker today is Dr. Samson Hegos. Samson earned his PhD in Atmospheric Sciences in 2008 from Cornell University and was a postdoctoral research associate at the University of Miami Rosenstiel School of Marine and Atmospheric Sciences before joining the Pacific Northwest National Lab in 2009. Samson's research interests are focused on the understanding and modeling of precipitation processes over a wide range of spatiotemporal scales, from the life cycles of individual convective cells to tropical intraseasonal oscillations, atmospheric rivers, and interannual to multi-decadal variations of monsoon systems. Samson, thank you so much for joining us. At this time, we will get the controls turned over to you.
Thank you, everyone, for joining this webinar, and Victoria and Sandy for organizing it. The objective of our work is to look at variability of MJO propagation across the maritime continent. Several people are involved in this project, many from PNNL and Chidong Zhang from PMEL. Okay, so to give you a sense of the problem that we are looking at, here we see the winter of 2018. We have 3 MJO events. The red one is October. You see it's effectively disrupted over the maritime continent. The one in November in green is amplified, and the one in December is also strengthened as it propagates across the maritime continent region. So the question is, what process control this variability that we see in the propagation of MJO events like we see here in the winter of 2018. So if you look at the climatology, you take MJO amplitude and plot the phase versus the months, you see something like this. You have several peaks, minima, maxima at various seasons and at various amplitudes. So how can we explain this rather complicated looking variability? We also ask the same question for the stalling of the MJO. How long an MJO event spends at a specific phase is also shows a lot of variability, as you can see on the far right end of the panel. So what process control this rather complicated looking variability in MJO propagation is the question that we wanted to investigate. So we take 2 approaches. One is to look at the MJO as part of the seasonal cycle of monsoonal moisture flux convergence, and see how these monsoonal flux convergences vary with the season, and hence influence the behavior of the MJO. And the second approach is to look at the impact of the maritime continent, specifically the fact that there is semi-annual variability in the insolation over the equatorial region. So to start to look at the observational perspective to estimate the role of monsoons, we look at the moisture budget. If you want to look at the moisture flux associated with precipitation patterns, we can take the moisture budget equation, get the convergence out of the imbalance between precipitation and evaporation, then we can solve for what we refer to as moisture flux potential. And you get the gradient of it to get the components of moisture flux associated with the given precipitation. So all you need to do that is basically high frequency observed precipitation. If you estimate the fluxes from that, then you can get the moisture fluxes. So we did that for 30 years of daily precipitation from Persian data set. So we estimate the moisture flux from that. We solve the Poisson equation, and we get something like this. So what we see here is basically moisture flux associated with the monsoons. So as you expect, in January, you have Australian monsoon season. You have divergence in red here from the South Asian, East Asian monsoon region going back to the Australian monsoon. And in July, you have a reverse patterns. Another important fact to note here is that the Australian monsoon region and the East Asian monsoon regions are at different longitudes. So what that means is this convergence is moving east and west as well. Now that's something we will come back to in a minute. And then we have the role of Enso in this context. So you solve for that as well. You see what you expect: strong moisture convergence over Central Pacific during El Nino season, and the reverse during La Nina season. This is in January on the left-hand side, and in February, in July on the right hand side. So you see this moisture flux toward the Central Pacific in January, and further also to the east and northeast in July. Now, if you look at the zonal movement of this convergence, you see this pattern. So the convergence is in shadings, and the contours are precipitation. So with the monsoon, you have eastward movement of this zonal component as well as the meridional component. But this movement is prominent in the zonal component. Now we can estimate the contribution of MJO patterns to this zonal movement of moisture convergence shown here. So as you can see, as this moisture convergence is moving from the East Asian monsoon to the Australian monsoon region, the MJO events, of course, are propagating faster. So what that means is they are moving from favorable environment to unfavorable environment, or from unfavorable environment to a favorable environment, just as part of that monsoonal moisture flux convergence. So one important thing to note is that the convection associated with MJO is a very large part of this monsoonal movement, and the non-MJO component shown on the right-hand side is makes smaller contribution. So what does this mean for individual MJO events propagating? So as I said, as moisture flux convergence is moving east and west, the MJO events are going in and out of that environment. So what you see here is MJO events tracked by precipitation from Zhang and Ling's work in 2017. This is tracking of MJO events using precipitation Hofmüller diagrams. So what you see is that in May, June, and July, you have the stronger MJO events on the eastern side of the maritime continent, but as they are propagating, they are moving into regions that are unfavorable for convection, so they are weakened. While in February, March, and April, they are starting out in a place where the moisture flux convergence is unfavorable, and they are moving into favorable environment, so they are growing. So you see similar behavior to a lesser extent during El Nino and La Nina season. So this is specifically just for the times where we have transition. And when you look at the winter and summer seasons, you see what you expect. That is, during monsoon season, you have stronger MJO events in general, in November, December, and January, and weaker events in August, September, and October. In this case, so the zonal variability comes from Enso. Specifically, as we noted earlier, over Central Pacific, you have strong moisture convergence flux, and you see that stronger MJO events further out to the Central Pacific. During La Nina, on the other hand, you have stronger favorable environment right on the western end of the maritime continent. So as the MJO events cross this zonal environment, they reflect the zonal structure of the moisture flux convergence. To make that point further, we can look at the Australian monsoon. So this is Australian monsoon index, defined as the zonal wind at the blue box shown here. And if you look at the propagation of MJO events and relate it to the strength of the Australian monsoon, again, you have the stronger MJO event during weak Australian monsoon on both sides of the maritime continent, while when the Australian monsoon is strong, they are in the middle. That is a red MJO event shown. So as you can see, the monsoonal variability is also reflected on the propagation amplitude of the MJO events as identified by Zhang and Ling MJO precipitation index. So that brings me to the next piece, that is the semi-annual variability of insolation over the maritime continent. To motivate that, let's look at the precipitation over land and ocean during different phases of the MJO at different months. What you see here is you have this peculiar feature of precipitation over maritime continent islands in phase 3 of the MJO in March. And you see that contrast also, a little bit of that is also apparent in August and September. You don't see that over the surrounding waters. Over the surrounding waters, you see what you expect, that is the monsoonal increases precipitation in winter. Those are the bottom panels. So that's something to keep in mind. Then when you take the soil moisture, you see similar behavior. You have wet conditions well ahead of the typical phase of the MJO over the maritime continent, that in this case, as you can see, in phase 3. So you have wet conditions in an otherwise dry environment just over the maritime continent land. You see that in different global analysis products. So that leads us to some hypotheses. That is, the semi-annual variation in solar insolation and initial soil moisture modulate the propagation of MJO across the maritime continent. Excuse me. So we, to test this hypothesis, we run some WRF simulations. We take an MJO case, a November case shown here. It's fairly strong MJO event propagating across the maritime continent. And then we ask a question, what would happen to the maritime continent precipitation if this event happened in a different season, in March, where you have insolation is strongest over at the equator? What would happen if it were in September, where you have stronger insolation over the region, but also dry land surface conditions? So we designed the experiment as follows. That is, we change the insolation at top of the atmosphere, top of atmosphere downwelling shortwave radiation by March values. And in the next experiment, we introduce dry soil conditions as initial condition. And in the third one, we introduce a combination of them. So what we find is that as you increase insolation, you get increased precipitation over the maritime continent islands. The effect of dry soil, on the other hand, is relatively limited. The reason is, as we look at the trend in soil moisture, it quickly recovers as the dry conditions themselves favor the convergence and the increased precipitation over the region. So the impact of initial dry soil conditions is relatively muted. But when they are combined with the higher insolation, as you can see on the bottom right figure, you see enhanced precipitation over the maritime continent islands. So what that means is, if you look at the Hofmöller diagram of precipitation, you see that enhanced precipitation over the maritime continent in both high insolation and high insolation plus dry soil conditions. So the presence of the islands is felt even more during high insolation periods, that is March and September. So what that means is, if you look at the moisture budget analysis, you can separate this total precipitation over the maritime continent region into the part that is associated with MJO. That means it involves low frequency variability in both moisture or in wind, or everything else that is happening over the maritime continent region. So what happens is you can identify the stalling, the apparent stalling, as just increased precipitation over the maritime continent islands, particularly over the during periods of high insolation. So that means the increased precipitation over these specific islands marked by dotted lines: Sumatra, Borneo, and New Guinea. So how do we explain this rather complicated looking variability in the MJO propagation across the maritime continent? So we identify two factors. One is the monsoonal movement that moves east and west, as we discussed it earlier, and then you have this double peak in enhanced convection over the maritime continent in March and in September. So what that means is when an MJO event is propagating across the maritime continent, it experiences different environmental conditions based on one, the monsoonal position of the moisture convergence associated with the monsoons, and two, the level of insolation over the maritime continent. So these two factors go quite a distance in explaining the variability in MJO strengths. Thank you very much. I welcome any questions.
Wonderful. Thank you so much, Samson. And yes, if anyone has any questions, please feel free to raise your hand and we'll get your microphone unmuted.
Samson, this is Sandy. I have a question. Can you hear me?
Yes, please go ahead.
Okay, great. On your earlier slide, you showed the impact of the Enso signal on the MJO propagation. Mm-hmm. I think it was slide 6 if you want to go back to it. I noticed that you mentioned in the July case, you're showing motion both to the north, to the east and to the north. How much of that signal, how much of that signal is the seasonality of the MJO, and how much, or I guess the reverse of that question is, how big does the northward propagation signal compare to what the seasonal northward propagation is that you showed in your next slide?
This one, or let me, we are looking at the.
Yeah, I guess I was taking the question from your introduction slide, but if you could talk to me a little bit about the seasonality versus Enso in that northward propagation.
This one, right? So
yeah, I have go ahead.
So yes, I think a lot of the fact that we don't see much impact on the impact of Enso in summer is the fact that the MJO signals are not there anyway near the equator. So the impact of Enso being more of an equatorial forcing is more prominent during the winter periods, as I show in this one, I think. So we don't seem to see a lot of variability on dependence of MJO variability, propagation variability associated with Enso in summer. Is the prominent signal appears to be the seasonality, which suppresses the equatorial propagation of MJO events.
Okay, so that signal that signal that you showed in the introduction really is more the seasonality of Enso, yes, or it's the seasonality of MJO than it is an Enso signal.
Yes, so it's the seasonality sort of tilts the convergence field. which otherwise is east-west. Let me right here. So if you compare the January and the July signals, the main difference is the fact that the convergence field is has shifted a little bit north in July, as you would expect, the fact that it's the warmer hemisphere now.
Great, thank you.
Got it. And it looks like we've got Courtney's question after all. She wanted to know, Samson, could you remind us of your model resolution? For example, how well was orography represented over the maritime continent islands?
Well, we run, we typically, in this specific case, is 3 kilometers. So we have run even coarser and higher resolution ones, even 1 kilometer too. So we found the 3 kilometer to be a sweet spot, given that we need to have a large enough domain and sort of try to resolve diurnal cycle. So this one is 3 kilometers, but we have coarser simulations as well.
Perfect. She says thank you. All right, we've got time for one more question, and I see Eric has his hand raised. Eric, I've just unmuted you. You may have to unmute on your side.
Okay, can you hear me?
Yes.
Great. Hi, Samson. So I was thinking about your last results with the model and thinking about an earlier paper by Peatman et al., where they showed that the presence of the maritime continent and diurnal cycle interactions actually caused the MJO to propagate faster eastward. And I think you're showing that it stalls over the maritime continent. Are your results in contradiction to Peatman's results, or is there something else going on?
No, it is what's happening is it gets let's see, we see that too. I thought I mentioned that if you look right here, this is what they refer to as vanguard precipitation. The fact that the MJO signal gets to the maritime continent island faster, earlier than it would otherwise be. So if you, that's what they, if you look at the ocean, which the bottom panels, and the land over top panels, you see that you get precipitation over the maritime continent islands in phase 3. While over the waters, it is in phase 4. That's what they refer to as the acceleration of the MJO signal by diurnal cycle.
All right, perfect. Yeah, I missed that. Thank you.
Thank you, everyone, for questions. And Samson, thank you so much for your presentation today.
Sure.
We are going to switch presenters now. All right. Up next is a presentation by Hedanqiu Bai. Hedanqiu received her undergraduate degree from Zhejiang University, China in 2016 and is currently in the final stages of her PhD with Dr. Courtney Shoemaker at Texas A&M University. Her research interests include the diurnal cycle over tropical land and its interactions with larger scale circulations using both observations and models. Hedanqiu, thank you so much for joining us. At this time, we're going to get the controls turned over to you.
Thanks for the introduction. I'm Hedanqiu Bai, and our research focuses on the topographic influences on diurnally driven MJO rainfall over the maritime continent. But before talking about the interaction between the diurnal cycle and the MJO, I want to first revisit the definition of the diurnal cycle. Sorry, the slide stopped. I think it's okay. So let's first revisit the definition of the diurnal cycle. The two figures show the diurnal cycle from trim GPM are merged hourly rain rate from 2007 to 2019. The solid line is the hourly rain rate, and the dashed line is the first harmonic. For these two cases, one is over the interior sea and the other is over the mountainous region of the West Sumatra. We can see that convection is pulse-like instead of perfect sine or cosine. This is because convection develops very fast. And in these two cases, the first harmonic will give a shifted diurnal phase as well as a weaker diurnal amplitude. In other two cases, for example, over the coastal ocean and eastern Sumatra, multiple peaks can exist. So for these two cases, the first harmonic may give false information about the diurnal cycle. Take the eastern Sumatra as an example. There are two peaks, one in the afternoon due to the land convection, one in the evening due to the downslope rainfall propagation. And the first harmonic, its phase is in between the two peaks. In general, the diurnal rainfall contains a larger amplitude and higher frequency components than the first harmonic. These two figures show a comparison of the diurnal phase defined by the time of maximum hourly rain rate and the peak time of the first harmonic. The two figures overall give the similar diurnal phase. However, the details are different. For example, in the first picture over the mountainous regions, the diurnal rainfall peaks 1 to 2 hours earlier than the second figure. Correspondingly, the nocturnal offshore rainfall also peaks 1 to 2 hours earlier than the second picture. And over the interior seas, the rainfall peaks in the early afternoon in the first picture, while peaks in the late evening in the second picture. So defining the diurnal rainfall by maximum rain rate gives different timing than the first harmonic across the maritime continent. While many previous studies have used the composite first harmonic as the definition of the diurnal cycle, we showed in our previous paper that the diurnal timing has implications for convective triggering in models, and the diurnal frequency matters to the shape of the gravity waves generated by convection. So using the new definition, we look at the lag days of the diurnal rainfall amplitude anomalies compared to climatology as the MJO passes for 60 MJO events from 2007 to 2019 with a horizontal resolution of 0.1 degree. And we take 90 degree east as day zero. Here, the diurnal amplitude is defined as the maximum hourly rain minus the daily mean. We take the daily mean as the MJO induced rainfall. On day -5 and day 10, we can see that changes in the diurnal cycle over land jumps ahead of the main body of the MJO, and there's contrasting feature on the west and east side of the islands, all consistent with previous studies, such as Pittman et al. 2014 and Sakiyada et al. 2020. So changes are still robust, even using higher resolution data set and a different diurnal cycle definition. However, taking advantage of this higher resolution data set, we can look into more details about the interaction of the diurnal cycle and the MJO. For example, the strongest contrast is observed in Borneo, while the contrast is weaker over New Guinea, and Sumatra does not show such a contrast. So these features can also be seen from the MJO harmonic phase. Taking the offshore region of Sumatra as an example, the time series of daily rainfall anomaly is represented by the MJO harmonic. Again, 90 degree east is taken as day zero. And the gray contours indicate the 500 meter elevation. The MJO induced daily rainfall on west side of mountains peaks before the MJO arrives, while the east side is roughly faced with the surrounding ocean, except Sumatra, which we'll explain later. To explain the contrasting features on the west and east sides of the mountains, we first need to look at the wind control on the rainfall propagation. This is from our recently published paper. We investigated the offshore rainfall propagation from Sumatra using BMKG C-band radar rain rate at Padang for 2018. This hot water is shows the average of all nocturnal offshore rainfall propagation events. The x-axis is distance from the coastline, and the y-axis is local time. On average, the rainfall propagates offshore at an average speed of 4.5 meters per second. This is a histogram showing the nocturnal offshore rainfall event counts by MJO phase. Most offshore events take place during phases 1 to 3 when MJO is active over the Indian Ocean or when the MJO is weak. Almost no offshore propagating events occur in phases 4 to 5 when the MJO is active over the maritime continent. This can be explained by the large-scale low-level wind. The figure shows the Arrow 5 900 hectopascal wind for 2018. The strongest westerly low-level wind can be found in phases 4 to 5. And this strong low-level westerly wind will prevent land convection from propagating offshore during the active MJO. I think this interesting topic of the wind control on the rainfall propagation was also mentioned in Dr. Joyce's talk 2 weeks ago, which is also consistent with our conclusion. So with that, I'll explain why there's a contrast on the west and east side of the islands. The left column shows the Arrow 5 low-level specific humidity anomalies and the 900 hectopascal wind. And the middle column shows the moisture flux convergence. On day -5 and day 10, strong westerly can be observed to the west of Sumatra. However, on day -5, the air is moister to the west of Sumatra. So the moisture air with the strong westerly will create strong moisture flux convergence near the mountains of Sumatra. Therefore, the diurnal cycle is increased. In contrast, on day 10, although there's westerly, strong westerly, but the air is drier, so the moisture flux convergence is negative. Besides, this strong westerly wind will also prevent the rainfall to propagate offshore. So the diurnal amplitude is decreased. And over Borneo on day -5 to the east, the air is less moist. And the strong west-easterly will also prevent the rainfall to propagate. So the diurnal amplitude on the east side of Borneo is decreased. The orography of Borneo also blocks this strong easterly from coming to Sumatra. Therefore, Sumatra doesn't show a strong contrast. On the day 10, to the east of Borneo, the westerly and easterly create strong moisture flux convergence. Therefore, the diurnal cycle is increased. As for New Guinea, because the topography is more horizontal, so the wind that are perpendicular to the topography is weaker. Therefore, the contrast is also weaker. Although we think that moisture determines the overall diurnal rainfall, the wind can modulate the distribution of the diurnal rainfall amplitude. For example, this is the case for June, July, August. On day 10, the distribution of diurnal rainfall over Borneo is north-south rather than west-east, as shown in the previous slide. This is because the orography over Borneo is not a narrow range as in Sumatra or New Guinea. So when the wind has more north-south component, it will modulate the distribution of the diurnal rainfall to be more north-south. Similar to what we did for the MJO harmonic phase, this is the corresponding harmonic amplitude. Over much of the ocean and the west side of the mountains, the MJO-induced rainfall variation is large, while the variation is small on the east side of the mountains, indicating that the east side of the mountains is less influenced by the MJO. And this less influence from the MJO can also be observed from stratiform rain fraction. Sorry, I think this figure shifted a little bit. So this figure is the climatology for the stratiform rain over the maritime continent from TRIM GPM precipitation radar. So we can see that, I think it's rotated, so this large amount of stratiform rain can be observed over the warm pole. And there's erroneously high stratiform rain fraction over the high mountains. This is because the precipitation radar underestimates the shallow precipitation and also gives false alarm of a persistent stratiform rain over this high terrain. From the lag days of the stratiform rain fraction, we can see that the main body of the MJO consists of large fraction of stratiform rain because convective systems are highly organized inside the MJO. Because of false signals over Borneo and New Guinea, we cannot really tell what happens over these two islands. But luckily, signals over Sumatra are clearer. So stratiform rain is blocked by orography of Sumatra, and the east side of Sumatra is less influenced by the large amount of stratiform rain. This can be explained by several factors. The first is the MJO detours around or is blocked by the orography. So it's harder for the east side of orography to have lifting motion. So the rain shadow will concentrate on the west side of the islands. The second is related to the zonal moisture gradient. This figure shows the climatological zonal moisture gradient along this cross-section at 2 degrees north. On the west side of the mountains, the zonal moisture gradient is always positive because of the rainfall propagation. So this positive zonal moisture gradient welcomes the coming of the MJO. However, on the east side of the mountains, the zonal moisture gradient is negative, again, because the rainfall propagation. And it's harder for the MJO to cross the east side of the mountains. And finally, we want to look at what part of the diurnal cycle has what kind of change with the passage of the MJO. To do that, we first subtract the daily rainfall from the hourly rainfall and divided the hourly rainfall into 3 clots. The nightly rainfall from 22 to 5 local time, the afternoon rainfall from 14 to 21 local time, and the morning rainfall from 16 to 13 local time. And similar to what we did for the daily rainfall, we also Fourier fit the diurnal rainfall with the MJO harmonic. Again, this is the case for the offshore region of Sumatra. From this figure, we can tell that evening rainfall peaks before the main body of the MJO. With the information of the relative phase of the diurnal rainfall to the MJO, we use the K-means clustering method with the phase of each of the diurnal rainfall as the clustering feature. So K-means clustering basically clusters grid points with the similar features into the same group. Here we have 3 groups, which means K equals 3. This is because the variance explained per K is the highest when K equals 3 in our case. And this figure shows the distribution of the corresponding groups. We also did a sensitivity test to include the amplitude of each of the diurnal clots. But it turned out that the amplitude does not influence the resulting clustering, which may be because that the sum of the 3 clouds is 0, so the amplitude of one cloud is constrained by the other 2. For the 3 groups, the nightly, afternoon, and morning rain peaks before the main body of the MJO, respectively. And from this figure, we can see that the mountainous regions over Sumatra, Borneo, and Indonesia are all clustered into the second group. And New Guinea is a special case, which we will explain later. So for the second group, clear skies over the maritime continent prior to the active MJO are conducive to afternoon convective development. So the afternoon rainfall peaks before the MJO. If you recall the lag days of the change of the diurnal amplitude, we can see that the increased diurnal amplitude is mainly contributed by this afternoon convection. Similarly, on the west side of the mountains, they are all in the first group. And from this figure, the nocturnal propagating rain on the west side of orography peaks before the MJO arrives, because westerlies are not yet too strong to inhibit westward propagation. Therefore, the evening rain peaks before the MJO arrives. And again, from the lag days of the diurnal amplitude change, we can conclude that the enhanced diurnal amplitude is mainly contributed by the evening rainfall. Finally, the east side of the mountains, as well as the ocean, are clustered into the third group, where the afternoon rain and evening rain are roughly in phase with the MJO. So this is the diurnal cycle on the east side of the orography. There are 2 peaks, afternoon peak and evening peak, which means these 2 peaks are both increased with the active MJO. And for the special case over New Guinea, it's actually consistent with the MJO harmonic phase, where the mountainous region is also clustered into the third group, and it's roughly in phase with the surrounding oceans. This may be because that, again, the orography is more horizontal. So except for a small tip here, which is clustered in the second group, the rest of the mountains may be identified with similar features as the east side of the mountains. So to wrap up, defining the diurnal rainfall by maximum rain rate gives more accurate diurnal phase and amplitude. And the diurnal timing and frequency matter to the convective triggering, as well as the shape of the gravity waves generated by convection. Diurnal rainfall amplitude on the east side of the orography lags the west side as the MJO passes due to moisture anomalies and winds. East side of the mountains is less influenced by the MJO. This is because on the east side of the mountains, the zonal moisture gradient is negative. Therefore, it's harder for the MJO to propagate to the east side of the topography. And the K-means clustering shows that there's a strong dependence in diurnal timing on whether you are to the west, over, or to the east of the mountains when the MJO passes. That's it. Thank you.
Thank you so much, Hajantio. Great presentation. All right, we'll take questions now, and I see that Kelvin already has his hand up. Let me get you unmuted there. You should be able to go ahead now.
Mute.
There we go.
I'm muted now. Yes, I also enjoyed your talk. I had one question. You very briefly looked at the feedback of the diurnal rainfall on the MJO by looking at the variation on east and west sides of orography. But can you quantify that impact? Will it have a big impact on the propagation of the MJO?
I think it's hard to quantify the impact of the diurnal cycle on the MJO only using observations, but it can be achieved by models. For example, in this case, we showed that the zonal moisture gradient on the two sides of the mountains may have different influence on the MJO. So maybe we can do some model tests to quantify the influence instead.
Okay, thank you.
All right, and I see Ping Ping has hand up.
Yeah, okay, this is Ping Ping Li from CPC. We reported our progress 2 weeks ago, which have some similar, did similar things and get some similar results. One question I have is that looking at, well, it seems you are dividing or classify the diurnal cycle patterns basically in two big categories: the afternoon peak and the evening peak. But well, based on our results, if you did not attend, you may check back, and some you have touched today. Really, the diurnal cycle the convection starts at the mountain top around the noontime and then propagate downward. And in the ocean side, then there is another line of convection propagate from ocean towards the land as part of the sea breeze, land breeze. So the diurnal cycle phase is really quite complicated depending on where you are talking about. It's not kind of purely afternoon or purely evening. Some places may experience two peaks. Some places may just experience one peak in the around the noon or late afternoon, depending on its location. So I'm wondering performing harmonic analysis, and then based on that harmonic analysis, you choose, well, you decide if or not this is the afternoon peak or morning peak. Maybe this is a oversimplification, and that will kind of cannot summarize or describe the overall situation. That's what I'm wondering about.
Yeah, thanks for comment. I think this is a very good point. So for this one, we only divided the diurnal cycle into three clots. Yes, as you said, to simplify things and to look at the overall features. But as you pointed out, yes, the diurnal cycle is very complicated. And in our previously published paper, we also noticed that the complexity of the diurnal cycle. For example, over Sumatra on the east side and west side of the mountains, the offshore rainfall or the outgoing rainfall propagation actually is in different local time. So the offshore rainfall propagation is later than the inland rainfall propagation. This is related to the land sea breeze circulation. So yes, as you said, it's a very complicated problem. So we maybe oversimplify things, and we will look more into details in the future.
Yeah, well, as a matter of fact, initially we're looking at the overall results, the mean climatology kind of things. The initial conclusion was to say there are two different types, right? One land types, one ocean types. Land mostly will have you see the peak in the late afternoon, the ocean early morning. But really, when you're looking at the detailed distribution in this maritime continental areas, the topography is very complicated, and the diurnal cycle is very interesting. The one common thing we found is that, well, over those big islands of maritime continental, one thing is common. The diurnal cycle basically is really composed of propagation of cloud bands from both the land, from the land and from the ocean. So therefore, it's not we think it's not appropriate to simply classify the dino cycle as basically just two types, kind of late afternoon type and early morning type.
Yeah, this is a very good point. We will look into it in the future. Thank you.
All right, I'm not seeing any other hands. So Hidancho, thank you again for your wonderful presentation. And it's great to see some interaction between the different projects. That's awesome. So with that, we will turn back over here. We would like to thank everyone for joining us for this set of presentations in our series of Years on Maritime Continent. I would like to thank today's presenters, Samson and Hidancho, for taking their time to share their work with us. And the recording of today's webinar will be available within the next week on our website, cpo.noaa.gov/cbp/webinars. Our next webinar will be on March 25th, 2021. We hope to see you all then. Thank you.